Hi guys, this is Miss King again, and in this screencast we're going to look at DNA replication. Alright, so DNA replication is a process. That means it's a step-by-step series of events that are going to occur. And this is going to happen in any kind of cell that needs to divide or go through cell division. When we make a copy of our DNA, we need to have an exact copy with no mistakes. Now, why do cells divide? Good question. A lot of our cells are going to be damaged just in the day-to-day, things that we do. If you get a cut on your finger, you've damaged millions of cells and they would need to be repaired or replaced. In order to make the new cells to replace or repair those cells, we would need a copy of our DNA. Okay. Also, when we grow, we're adding new cells to our body, so we would need to make new cells for that as well. Alright, so let's take a look at our steps for replication. The first step that needs to occur is we need to unwind or untwist our DNA ladder. Okay, so we would make it flat, sort of like this picture. And we would need an enzyme to help us do that called DNA helicase. Hela stands for helix, which is the twisty structure. And remember, ACE is enzyme, and DNA because it's working on DNA molecule. So DNA helicase is what we're going to use to untwist our DNA. The second thing that's going to happen is we have to unzip the DNA, which means we have to break the hydrogen bonds between our nitrogen bases. What we're going to have to do is create what's called a replication fork. So right here would be our, let's label it replication fork. And we're going to use DNA helicase to do this as well. So while the enzyme is untwisting the DNA, it's also going to be pulling it apart by breaking those hydrogen bonds. All right, now step 3, we're going to start forming our 2 new DNA molecules by adding complementary base pairs to each side. So each one of these little base pairs is going to have its match come in and reconnect with a new hydrogen bond slowly, one base at a time. Okay, and we're going to use an enzyme called DNA polymerase to help us with this step. So DNA, because we're building a DNA molecule, polymer stands for the building blocks of DNA. The DNA is our polymer, so we're building a DNA molecule, and again, ACE is enzyme. Now, when we do this step, we're going to end up going in opposite directions. So this side of the DNA is going to go this way. So each base pair will come in one at a time, and it will go in this direction. And on this side of our DNA, we're going to go this way. Okay, so each base pair will come in this direction, one at the time. We have a term for this, and that is anti-parallel. Anti-parallel means that the molecules are going to be built side by side, but it's going to go in opposite directions. So that we can kind of see what anti-parallel is, we have what are called 5' and 3' ends on our molecule. The 5' end is going to have a free phosphate. So right here is our free phosphate. So this would be the 5' side of our DNA. And over here we have a free sugar. So this would be our 3' end to our DNA. So anti-parallel just means that we're going to go in opposite directions. So we always go from 5' towards 3'. So when we build our molecule, we have to go in this direction on this side and this direction on this side. Okay, and that's why it's going to be anti-parallel or going in opposite directions. Now, because we have to go in opposite directions from 5' to 3', that's going to give us what's called a leading strand. So basically on our 5' side of our DNA, it's going to be one continuous process. So these these nucleotides are going to come in one at a time and go slowly in this direction in one continuous strand. Now, on the other side, because we're going in the opposite direction, we're going to have what's called the lagging strand. And we call it the lagging strand because it's going to connect our base pairs in fragments. And those fragments are called Okazaki fragments. So these bases will come in and make a little fragment, a little section, and then they'll skip a section and they'll make another little fragment or another little section. And those are our Okazaki fragments. Eventually, all of these base pairs will be filled in. They're just not doing it in a continuous manner. All right, and then the last step to our process, we will end up with two identical, what we call daughter strands. So each one of these is a new daughter strand of DNA. And they're going to be what we call semi-conservative. What that means is half of the DNA molecule is old or original, and the other half is the new side that we built in one of the previous steps. So for on this particular DNA strand that we have, this side would be original, and this side would be original, but this side and this side would be our two new strands. So half old, half new. Once this process is complete, once we have our daughter strands of DNA, cell division can continue and we can make new cells for whatever reason we need them. Any mistakes that occur during this process are going to need to be corrected by other what we call proofreader enzymes. If those mistakes are not fixed, then we're going to have what are called mutations. That means changes in the DNA that are not supposed to be there. There's lots of things that can cause mutations. Those are called mutagens. Anything that causes a mutation is a mutagen. And those are things like viruses, chemicals, radiation, lots of different things. All right, and that is the process of DNA replication.